So welcome back, everybody, and welcome to the session this week. And I'm going to quickly set up the sharing of the screen and try to give you a guide over what we are going to do this week. So this is the PDF file. And as you probably noticed now, I use the Jupyter Notebook as a kind of companion. Now, today, I actually wanted to go a little bit more into the details of topics which we glossed over last week, because then we were more interested in setting up the general structure of a quantum neural network. And one of these technicalities is about input code encoding. And in particular, since many of you are probably interested in using classical data, the question then is, how do we encode classical data? You also have the cases of quantum data, but this is something which, for most of the applications of quantum machine learning, people have essentially taken classical data, which could be financial data, it could be images which you want to train and be able to make a prediction of whether that is a specific type of object or not. Then there is another technicality which I wanted to discuss. And that deals with the optimization part. So remember now again that these quantum neural networks are entities which you can view as a variational quantum circuit. So that means that we will have one step where we encode the information, which is section 2 here. And then there is another step where we actually, after we've done the rotations and introduce the quantum computing parameters, which we want to optimize, that's the variational part of the circuit, then we need to calculate gradients. And that means that the type of calculations we typically run are hybrid calculations, exactly like we did with the variational quantum eigensolver. Now, for the gradient computation, the parameter shift rule is the same as we use for the VQE when we calculate the gradients. So that means that we have the same circuit, except that we need to calculate the quantity which we're interested in for an angle plus pi half and minus pi half. So we have an exact expression for the gradient. However, what we did in project 1, in order to simplify things, we use normally what's called a plane gradient descent, which means that we take the gradient and instead of having an expression for the second derivative, which leads to what in optimization theory is called the Hessian matrix, we replace that with a constant, which normally is called learning rate in the machine learning literature. Now, there is a possibility to calculate this one using what's called the Fisher information. So some of you may have studied the mathematics of quantum sensors, and there you probably heard of something called the quantum Fisher information. And this is the quantity which I will actually spend parts of this lecture on. Now, one other thing which we are going to do today is actually go back to some of the codes which we had in the Jupyter Notebook from last week. And in the Jupyter Notebook from last week, you have an example of a quantum neural network where we fit a function, a simple polynomial fit, and another case which is a classification problem. And I wanted to go back to those programs from last week, essentially because the benefit of using quantum machine learning is actually that you use much, much less parameters than you would do with a classical neural network. So the benefit is essentially in the fact that you have a variational quantum circuit with fewer parameters than you would have in a classical neural network. Now, there's a huge field of activity in quantum machine learning, which spans from the applications of quantum neural networks to the solution of differential equations. So if you look at point 5 and 6, we're actually going to introduce how we can solve differential equations using quantum pins. So that's the variant, the quantum mechanical variant of a classical physics-informed neural network, which many of you have encountered. So if you in project 2 are exploring the HHL algorithm, and you apply that to the solution of, let's say, Poisson's equation. There is an example in the notes here where we actually use quantum pins to solve the same differential equation. So most likely I will probably need sometime next week as well to discuss the implementation of quantum pins. Okay, any questions to the plans for the day today? So if not, I'm going to go back to the whiteboard for at least this lecture, because I wanted to actually discuss the gradient computation. And the gradient computation leads also to the parameter shift rule and this Fisher information, which is something which some of you may have encountered if you've taken a course on quantum Monte Carlo methods. This is normally called stochastic reconfiguration as well. So this quantity is something which enters many, many fields, but where the main issue or the main topic is optimization. Okay, so let's switch over to the whiteboard and try to bring up some of the details which you will also find in the slides. So the beginning now, I just wanted to quickly repeat some basic things which we have in the slides, so that we are on the same page, all of us. So if we look at the quantum neural network, which we simply shorten to QNN, the basic thing is that this is to be viewed as a quantum variational circuit, or a quantum parametrized circuit, or variational parametrized circuit. So these are different names which you can use. So the typical function which you end up evaluating, x of some parameters theta, so x could be your input variables. This is given now by three quantities. One, which we call u of theta, and that is where we have the variational parameters. So this is a unitary transformation. So let's just write this down here. So this is called the variational ansatz with trainable parameters. Variational ansatz. And that has trainable parameters like this theta. So theta would then be a set of parameters, theta 1, theta 2, etc., up to some theta p. They are normally real parameters. But you could also have them as complex, but they are normally real parameters. So these thetas, theta I is normally a real parameter. Then we have another unitary transformation, which is normally called the feature map, which encodes the data into a state which we then can use for quantum computing manipulations. So this u of x, if we now just put a new arrow, this is normally called the feature map. So this could be the classical data which you have, the pixels of an image. That image could be a painting of Van Gogh or not. Or since we are in Norway, we are painting of Grieg. And then you would take the pixels which represent that painting and translate the pixels into a quantum mechanical state. Now, the problem you see here, if you do that, this deals with the encoding part, which is a tricky part in the implementation of a quantum algorithm. If you take an image like the MNIST data, which some of you have encountered when you've taken a course in machine learning, the scaled down data contains 8 times 8 pixels, which means that you have 64 entry points for an image, which is a gray image. And in that case, if you translate it in a brute force way into a bit representation, you would actually need 64 qubits to encode that information. And that's a lot. So typical quantum computers which you can access nowadays have between 20 to some 100 logical qubits. So this u of x is normally called the feature map, and that is the one which encodes the data. So data encoding. And we will, after the break, we will look at separately how we encode the data. So this is a data encoding. And then this acts on an initial state. And the typical case is you having an initial state, which is then prepared in the qubit 0 state. So this is the final state. And if you look at the circuit, if you take 2 qubits, so this 0 is just the initial states. So with 2 qubits, and then we have some observable. When you did the VQE, the observable was the energy, the expectation value of the energy. The observable, if you are doing a classification problem, that could just be a binary problem of the type yes, no, true, false, 0, 1, etc. So that would be the observable you're looking after. So if we have an example with 2 qubits, the way you would have this is now you start with a qubit 0 and qubit 0 here. And then we have this phase, which is the encoding phase. So this is the U of X. And then this is normally done by some rotation. And I'm just writing this as an R of X. And then we have some X1. So now we have 2 data, X1 and X2. And then we have a new one. So there is no entangling, no nothing here. And then we have transformed the data into, let's say, a bit string, which in our case will be a qubit string. Then we have the next phase, which is then the variational part. And this is the one where we also have the hybrid connection with the classical optimization algorithm. So this is the U of theta, which we call the variational part, where we have all these parameters. And here now you can actually make this as deep as you want. So this, what you're having here now, the U theta, is the equivalent of the classical hidden layers. So the U of X is actually you taking the input from a classical case. And in a comparison with a classical neural network, this U of X corresponds to you setting up the input. So you could think of U of X as the input layer. Now, the variational part is actually your hidden layer. And you can see now that in this specific case, if I now just have an Ry with a theta 1, and here I can do an Ry rotation, exactly as we did in the VQE project, then we can have a C0 gate where we now entangle these 2 qubits. But then there is nothing which limits us in making this circuit deeper and deeper. So we can have an RC with a theta 3, and I can have an RC here. I can have an RX with new angles. So this is an RC with a theta 4. Sorry for this. Let me just try to make this a little bit larger here because it didn't. Sorry for the for this one. Like that. And then we have a new one here. And then we have an RC with a theta 4. And then we have a new RC. And you see, you can actually construct this deeper and deeper. And the more parameters you have, clearly more flexibility you have, but the heavier the training. So this would be the length of the circuit. And at the end, you make an observation. So you make a measurement. And this is the final part. And then you have the observable here, which I just call for an O here. So if you look at the basics here, this U of theta is actually going to be given by a set of typically products of different gates. So we have parameters E of theta L, and then we have P of L divided by 2, multiplied. And what I'm doing here in this equation is that I'm leaving out the C0 gates. So when you do this kind of training, what you could do is actually to see what happens if you leave out the C0 gate. So keep in mind that the C0 gate does not have trainable parameters. So this is pretty close to what we did with the VQE, except that then the observable was actually the energy. And in the VQE, we didn't need this encoding part. We simply took a state, a 1-qubit state and a tensor product of those with the random initializations on the block sphere. And then we simply added as many C0 gates as we wanted. If we didn't do that, then the wave function would just be a product function of these rotations, a product functions of individual qubit states. And if you have strong correlations, this would actually not give a very good result. So when you play around with the quantum neural networks, in a certain sense, your depth of the network mimics what you do with a standard neural network, where you can play around with many different hidden layers. What you see here, compared with a standard neural network, is that the number of parameters can be much, much smaller. And you will see that in the examples which we had from last week, which I will bring up after the break. Now, so this would typically be given by something like this, and this P of L's. So keep in mind that here, I'm actually leaving out the, so this P of L is then just given by a set of Pauli gates. And this can be set up as a tensor product of different Pauli gates. Then to calculate the derivatives, so the gradient in the optimization part. So the optimization part that includes a function. So if we have a function which we suppose now that the loss function or cost function is given by the mean squared error. So we could have something like this as a sum over all the data which we have. And then we have a f is now the function which we fit from the neural network. And we have some target value y. So we have an input is some pair of values, can be x of k and y of k. So we have some input value x and an output y of k. So this is input output, the variables which we want to find a fit of. So this f, which you see here, is actually the function which we are using as a model. So in our case, this is the quantum neural network, this f. So when we look at the optimization part, what we will use again is the parameter shift rule for the gradients. So let me quickly remind you of these things here. So that means that the function which we need to optimize is a function of this f here, which then is going to give us an f, and this is an exact formula, which we also applied when we looked at the VQE algorithm. And we have to do this, so we're going to put a k here and a k. So we have to do that for all the parameters which we have. So if you look back at that 2-qubit network, we have 4 parameters, and we need actually to evaluate the shift rule for 4 parameters. There is no need to actually set up any new circuit because the circuit is actually given by this function f. This is our circuit, okay? So it's pretty similar to what we do with a standard neural network. Now, there is something which we can do when we do the stochastic gradient descent. So if we go back a little bit to the standard gradient descent, which we implemented in project 1, when we looked at the VQE, then if we just do a gradient descent, what we get then is that the parameters theta, and now I'm just writing them as vectors, so I don't put a subscript. They were given by the values from the previous iteration minus, and then we had a parameter eta, which is the learning rate, and then we had the derivative or the gradient with respect to the loss function n, which in our case is actually this function, which we have this function f, which is f here in the notation which I put up here. So essentially what you end up is actually taking the derivative with respect to this function f, which is the network. But this is a little bit more general what you see here. Now, this is the standard gradient descent. You could also use quasi-Newton methods, and many of you did actually implement that, like methods like Kubila, you have Broyden's method, and other types of methods which are called quasi-Newton methods. The brute force approach is then to fix this learning rate, but we also have other ways of doing that, and you will see in the codes which I have for this week and for the last week, you will find famous optimizers for the learning rate like Adam, etc. Okay, so this is the basic ingredients which we need, but in this field, there is something which is called a natural gradient. And this is actually a preferred quantity for this type of variational optimization problems. And this is intimately linked with a concept, if you are familiar with variational Monte Carlo calculations, which is called stochastic reconfiguration. So I'm just gonna, because these are used interchangeably. So what that means is the following. That means that we are going to have a theta which is being updated, and now this is a vector, and this is given by the previous value, minus, there's going to be a parameter which I'm going to call gamma, which I will derive for you just in some few moments. And then there is a quantity which is called the Fisher information, multiplied with a gradient of the cost function. So this is called the Fisher information or natural gradient, Fisher info. So there are many names of this quantity. If you do standard classical variational Monte Carlo calculations, this is normally called the covariance in the stochastic reconfigurations. So we need to go through some of the steps and how we actually get this quantity. So this quantity is meant, F is a matrix which approximates the full Hessian matrix. So I know that not all of you may have taken a course in optimization theory or you've taken a course in machine learning, but the full Hessian matrix is actually the matrix which contains the second derivatives of the cost function. So that means that we will have terms with a derivative with respect to theta, the parameters, but for the second derivatives. And this matrix is actually something we try to avoid to compute. And there are ways by which we can do that. And this stochastic reconfiguration and Fisher entropy is actually one of these quantities. Now, I'm going to derive this expression here, the natural gradients, and you will see that in the codes which we have, you will see implementations of the natural gradients. And this often gives better results than a standard optimization. So this is a technicality which we are going to deal with. So this part here, the natural gradient, is the first part which we'll deal with. And then the next part is input encoding. So I told you in the beginning of the lecture here that today we are going to look a little bit more at the details of some of these details. So natural gradients is one of the technicalities in the optimization part. And then the other technicality deals with the encoding piece. So when we have the encoding piece and the natural gradients, then the variational part is actually us repeating what we did with the VQE. So that is essentially us having different rotation gates with C0 gates, and the depth of the quantum neural network is simply proportional to how many such gates we want to implement. Okay, does that sound clear? So today we are going to look at two essential parts. One is the encoding of the data. There are different ways of doing that, and some more complicated and some easier. And then we are going to look at the now first at the calculations of these gradients. So let me bring up the discussions of this type of gradient. So let's now look at the VQE case, because that's the simplest one to catch. So this is a VQE parallel. So keep in mind now that your neural network, the quantum neural network, is a lookalike of the VQE which we did, except that you have this encoding of the data part, which we did not have to deal with when we looked at the expectation value of the energy. So let's now stay with that. So with the VQE, what we have is a variational ansatz for the wave function. And this variational wave function is a function which may not be the exact solution. It depends on the parameters theta. And again, this theta contains now a set of parameters, and they are normally real parameters, up to some theta p. Then I have a normalized state. So when I normalize this state, I'm going to put a bar on top of it. So this is a normalized state. And the normalized state is us simply calculating this quantity here. So some of these statements here first are actually pretty trivial. But when you see this bar notation, that is simply the normalized state. And then in the VQE, what we calculated was actually the energy as a function of theta. And we ended up evaluating this quantity here and optimizing that quantity. So we have a Hamiltonian, psi of theta, and this is divided by the norm. This is essentially what we did in project number 1, okay? So I'm just using this as a typical example because when we come to a neural network, we're actually going to look at another type of observables. So in the VQE case, we had the expectation value of the energy. Now, when we do a neural network, we're actually going to look at the output of the neural network, which we're interested in, which could be us having a binary output, true, false, etc., etc. Now, there is a technicality here, which often is written with an acronym with TDVP. So time-dependent variational problem. And this leads to, so this is a technicality which I'm going to labor a little bit on now. So a technicality, which is an intermediate step in order to derive these natural gradients. So this is called something which I'm going to label for the exact imaginary time evolution of a state. So what we have then is that we define a variable tau, which is actually the imaginary time. So in a sense, what we are doing is to rotate the time into the complex quadrant. Now, this is the basis for those of you who may have encountered something which is called diffusion Monte Carlo. So if you rotate time in Schrödinger's equation, Schrödinger's equation becomes a diffusion type equation in complex time. And that is the basis for what is normally called the kind of exact benchmark many-body method, which is called diffusion Monte Carlo. And I will show you why that can give you the exact solution here. So that means that the state then, psi, and this is a state as a function of imaginary time. So we are assuming this is the exact wave function. This is now given by minus tau. We have the Hamiltonian acting at the state at time equals 0. So I can expand if I now have the exact energies. So suppose now that these are available, I can expand the initial state in that set of states. So this is given by a sum of all these coefficients. And if I have a finite basis, this is a finite sum. So that gives us the time evolution of the state, this imaginary time evolution, which is then given by n of C of n of E minus tau of E of n times n. Because now the different states n are actually eigenstates of the Hamiltonian. Now, what is interesting now, if this C0 is different from 0, for large times, we can then, if we have assumed that E0 is the lowest lying state, we have this ascending series, then the imaginary time propagation for the ground state is going to be dominated by the state with the lowest energy. So if I let tau go to large values, what I will get then is that psi of tau is proportional to E minus tau of E0 times 0. So what you can say then is that this imaginary time propagation actually filters out the exact ground state of the system. So when you do a variational calculation like the VQE, we do normally not evolve an arbitrary state in the full Hilbert space. So we are normally restricting ourselves to some kind of variational manifold where the solution lives. And that exact state may actually not be something which belongs to that set of variational states. So this is something to keep in mind. And you saw that when you implemented the VQE. For those of you who did not entangle the qubits, you would just get a set of product states. And even if you had many variational parameters, you would never get the exact state. So what we are, in general, the exact state may not correspond to the set of variational states which we have. So what we are going to look at now is the idea of something which is called stochastic reconfiguration. And I'm going to shorten that with an SR. So SR stands for stochastic reconfigurations, or, and this is actually equivalent with natural gradients. So we are going to look at a small infinitesimal imaginary time step. We are going to project the resulting state back onto the manifold of variational states. And then we are going to interpret this projection as a parameter update of theta going to theta plus some delta theta. So let's take a look here at some minor technicalities. So let's do a small time step, delta t. And what we are going to do is just to keep terms to first order in delta t. So for small time steps, this minus of delta t tau times the Hamiltonian is something which we can then write exactly out as a delta tau of h plus O of delta tau squared. So it means that the exact propagated state and now we can use an ansatz. So I'm just going to call this psi of exact. This is now approximated with 1 minus delta tau times the Hamiltonian, but then I let this act on the manifold of variational states. So keep in mind now that this psi of theta here is an approximation to the exact wave function. It's a variational state. So I want you to keep this in mind, because whatever we do with these variational quantum circuits, we are actually dealing with an ansatz for the state. So the variational parameterization of the circuit is an ansatz to the exact state. So I'm now setting up this in terms of that trial wave function. Now, there is a small technicality which I'm going to mention. So we have a first order norm preserving form, which is useful technically. So this is a technicality preserving form, which is going to be given by this psi exact, which is approximately equal to 1 minus delta tau, a small time step. And then I have E minus this energy of theta multiplied with the state psi of theta. So if I subtract this E of theta, that removes a trivial component which is parallel to the exact solution. And you can see that. So you could ask, why subtract? This is actually used as a trick in diffusion Monte Carlo calculations in order to avoid that you have to simulate for infinite times before you find the right solution. So what I'm doing now, this is the exact energy, so this is not E of theta. So if you do that, and you take the Hamiltonian, this is actually the energy with the exact here. And then we know that if I take this quantity of H minus E then, and multiply with psi, this is equal to 0. That means that the vector which we have then of E Hamiltonian minus E multiplied with psi, that is orthogonal to psi. In the sense which is relevant for norm changes to first order. So that term which we had, this term here, is actually moves the state in a direction which is tangent to a projective Hilbert space, removing trivial norm scaling or norm rescaling components. So this is just a small technicality which is often used to both remove undecided components, but also to take and have a guess for the energy, which brings you closer to, so this E of theta is often used in diffusion Monte Carlo calculation as an starting energy, so that you have a good guess for the energy, and that leads often to a better convergence of a Monte Carlo calculation. Now, what we do now is that we expand this wave function. So we have the wave function which depends on the parameters theta plus some delta theta. So we perform a Taylor expansion, and this is obviously given by psi of theta plus, and then I have a sum over k. And since this depends on many parameters, we are going to have derivatives with respect to theta k or psi of theta plus higher order terms. Like that. Then I'm going to define the tangent vectors. And these tangent vectors is a quantity which I will just label as a psi of k. So these are quantities which then depend on these parameters theta. And this is given by psi of theta. So that means that I can actually rewrite that term here, which you see here, in terms of this quantity psi of k. So that means I can replace this one with psi of k here. Okay. So this is just a notation which I'm introducing. So what we're going to do then is to compare the following. So we have the variational function. This is our ansatz, which we now approximate to psi and of theta. Sorry, it's psi of theta plus, and we keep only first order terms. First order only. So this is an approximation which we are going to make. So these are first order terms where we now have a delta, theta of k, and we have this psi of k, which we defined previously. And then we compare that one with this exact time evolution, imaginary time evolution, but where we have made a truncation to first order in delta t. So this is going to be given by 1 minus, and then I have this delta tau of h minus e. And now I'm just skipping this because now I'm looking at this in terms of the psi of theta. So this is an approximation to the exact one. Then I'm going to define a difference, delta, which is going to be given by this psi variational minus the psi exact. And what I want to minimize now, I want to minimize this difference. So I want to minimize a quantity I'm going to label as a d, which is actually this quantity here. So in a sense, this is what I'm doing now is to minimize the distance between my variational ansatz and the exact one, where I now have taken an imaginary time evolution to an approximation in terms of small time steps to the first order term delta t, but I multiply this one with an ansatz which I have. So I'm assuming now that this variational function is something which I can construct. So the psi prime variational is actually my parameterized variational quantum circuit, or just a parameterized quantum circuit, as we often call it. So the psi var here, the variational one, is our quantum circuit. And for the VQE, this is just simply the same circuit which we put up in the VQE. For a quantum neural network, we also need to include the encoding part, which we haven't touched upon yet. So what we want to do is actually to minimize that part. And that leads to, when we set it up now, I'm just simply setting them up. I compute, I take these two terms. So that means this term minus that term. And then I simply calculate that one. And I keep only terms to first order in delta tau. Okay. So it means that if I now look at this d, and now I keep only to first order, it's actually not so difficult to see the answer to first order in delta tau. What we are going to get then is the following expression. So I get a term which is going to be equal to a sum over ij. I'm going to have a delta theta I, delta theta j, multiplied, and remember now that these are the derivatives of the function, or the variational function with respect to the parameter theta I and theta j. So that's the first term, plus a term which is given by 2 delta tau, and then it has a sum over delta. It's actually not so difficult to see that when we only keep terms to first order in delta t. And that is going to contain a psi of I, and then I have h minus this energy, and then it contains a psi of theta, like that. So that's the term which we then want to optimize. To optimize means simply we want to minimize it. You can actually show that this is actually a convex function. So when we optimize it, with respect to the parameters, see, oh, I'm a little bit slow here. So let me just set this one up, and then we take a break. With respect to this parameter, then I get a d derivative of this function d with respect to the parameters delta, this small change of delta I, and that gives us then a factor of 2 of j of psi I, psi j, multiplied with delta theta j, plus 2 times delta tau, and then I have the real part. It's actually not so difficult to see that, of h minus e multiplied with psi of theta, like that. And that means, since we want this to be 0, because we are minimizing, so that means that we end up with a projected imaginary time equation in the tangent basis. So this is, and then we take a small break after this. So we get a psi of I, psi j, of delta theta j equal to minus delta tau. And then I have the real part of psi of I of h minus e multiplied with psi of theta. And this is a projected imaginary time equation in the tangent basis. So the derivatives of the variational ansatz in the tangent basis of psi I. So these are the derivatives of the wave function with respect to those parameters. So that's the stationary condition which we want to fulfill. Then after the break, we are going to set up the final expression for these natural gradients, because this equation which you see now is going to give us an ansatz for calculating the Hessian matrix. Now, when you see implementations of neural networks, you will often see two approaches. One, where you simply use a classical optimizer with Adam or root mean square propagation and so on, or alternatively, where we are going to use what's called the natural gradient. So the natural gradient is something which also leads to less parameters, and it's normally the favored approach in quantum neural networks. But there is nothing which hinders you, and I have comparisons in the lecture notes this week and also in the previous week, where we use a standard optimizer like Adam and compare that with the so-called natural gradients, which then actually follow the variational ansatz which we are setting up. And these natural gradients can actually be calculated with the parameter shift rule. So they can be calculated exactly. So there's no need for an optimizer like Adam or root mean square propagation or just a plain brute force gradient descent. So it sounds like a boring technicality, but it is extremely important in the implementations of the quantum neural networks. And you will see that in the literature when you dive into it, that this is actually a topic which people have been discussing up and down in the last years. Okay, I went a little bit over time, but I wanted to do this. And then after the break, we're going to wrap it up. And then we look at the encoding of the data. And then we go back a little bit to examples. And then we move over to quantum pins and look at how they differ from a standard physics-informed neural network. So let's do a coffee break or tea break. So what I wanted to end now within the next, hopefully 10 minutes roughly, is actually this discussion about the so-called stochastic reconfiguration, or what's normally called a normal gradient. So what I'm going to do now is to also remove redundant components which are parallel to the solution psi. So I'm going to introduce a normalized tangent vector. So let me just remind you of that, of the normalization. So this psi of theta. And now for the simplicity, I'm just going to write it as psi. Okay. And this is not the exact, because the exact will have a subscript exact on it, okay? This is just a simplified notation. So that means that I'm going to have a normalized state, which is simply psi divided by square root of psi times psi. And the normalized tangent vectors this is now given by a psi of k. So this is the derivative. Just to remind you of that quantity, this is a d of d theta k, the parameters of this normalized object. So when you see only psi now, that is a psi which depends on theta. And that means that this projected equation, which we had on the previous in the previous lecture, is now actually going to be given by psi I here, the normalized quantities, and then I have a delta theta of j, which is equal to minus delta tau, multiplied with this expectation value, psi of I, and h minus e. And now remember now that on the ket side, we have psi of theta, which I just shortened to. And this form is actually the one which is going to lead to the natural gradient or the stochastic reconfiguration metric matrix. In order to see that, we need another small digression. So this is today is a day of digressions. So small digression. And I'm going to introduce a quantity which is going to be pretty convenient, because at the end, we are calculating expectation values. So in project one, we calculated the expectation value of the energy. So I'm going to define a log derivative of operators, or log derivative operator. So I'm going to define a quantity O of k, and this is a quantity which depends on x. Remember that it lives in configuration space. And I define that as 1 over psi. So keep in mind now that psi depends on theta also, but I have suppressed the theta dependence. Sorry, not an equality sign, but d of psi of x divided, with the derivative with respect to theta k. And this is nothing but d of ln of psi of x of d theta of k. Okay, this is just an intermediate trick. So the kind of probability which we are looking at for VQE, which we had, the probability which we defined, the probability is we have a probability of finding the system in a specific state. This is psi of x squared and divided by psi over psi. This is the normalization constant. And then in statistics, we can then, since we have the probability, we can set up an expectation value as a sum overall if we have a discrete set of observables. If not, we have to replace it with an integral. So this would be the classical expectation value. Now, the reason why I'm bringing these quantities in is that you will see that this normalized gradient is actually proportional to a covariance. So if I use these normalized states, what you will see then, so this psi of I, these are derivatives of psi of j. It's actually not that difficult to see that. If you now go back to this definition of the operator, you can actually show that this is given by this quantity here. No, sorry. This is not, this is an expectation value. And if I have a real wave functions. So this leaves also the classical case and real parameters and parameters. Then you can define a quantity which is actually called the stochastic reconfiguration metric matrix, or actually it's going to define the natural gradient minus OI, OJ. This quantity here has a famous name in statistics. Does that ring a bell? Have you seen that before, that quantity? These are three expectation values. One is the mean value of this quantity OI, and the other one is the cross term of the two quantities. If I have I equal to J, this is the variance. When I is different from J, that defines a covariance. So what we have then is that this Sij is the covariance matrix of the logarithmic derivatives of the log derivatives. So this S actually measures how the parameters change, or the changes in the parameters alter the normalized state. That's one thing. This S is actually a metric tensor on the manifold of the variational parameters which we have. So it's actually going to define a tensor which we can use to actually define. So since it measures how parameters how parameter changes alter the normalized state. You can also show that it is positive semi-definite. And if you think of the energy expectation value, so if you now look at this other quantity which we had in this equation, where we have H minus this variational energy times the normalized state, we can also define a quantity which is called the local energy of X, which is defined as 1 over psi, this normalized wave function of X, with H acting on psi bar of X. Then I can actually define a quantity which I'm going to call for G or E of I, which is given by the real part of the term we had before the break of psi I of H minus the Hamiltonian minus this energy E times this normalized wave function. And that is nothing but the expectation value of this log derivative of EL minus the expectation value of this log derivative of EL, which is the energy expectation value we are looking after. So this G of I, this is actually given by the derivative d of EL as a function of d of theta of I, multiplied with a factor of a half. You can actually show that. So G of I is the covariance between the logarithmic derivative and the local energy. And this local energy is actually the expectation value which we get from the VQE calculation. You can actually show that. So if we put everything together, what we are going to have then, putting things together, what we have then is J of Sij of delta theta J is given by this minus delta of tau times the gradient. And this Sij is this log derivative covariance. Which is given by the variational wave function which we have. So when we are calculating the gradients now, and if we put this together, we have a g of I is then equal to, no, not theta, but O, the log derivative, OI of EL minus OI times the expectation value of the energy. And that means that when we are setting up a gradient descent now, if you think of a standard gradient descent for the energy, so for energy, what we have then is if we look at the gradient descent, standard gradient descent, what we have then is that the parameters theta are then being updated. So I'm setting this as a vector. So this contains all the parameters theta minus some parameter eta multiplied with this vector g. If I now instead look at what I have derived, so this is a gradient descent, and then what we have been doing in project 1, and you will see that in the codes for both last week and this week, that you can perform a standard gradient descent with an optimizer like Adams. So you replace the fixed learning rate eta with a standard optimization algorithm like Adams, root mean square propagation, and so on. So this would be the standard approach. And I'm going to write the GD standard plus variance with different optimizers. So that could be Adams, etc. And you will see when you look into the codes, this is something which I have implemented. But then what I can do is to use what's normally called a normal gradient, or in this case, stochastic reconfiguration. So SR, normal gradients. And in that case, I have an update now where I have theta, which is being updated by a new formula where I have a delta tau. So I have to fix that step. That is the time discretization which I'm doing. But then I have the inverse, that matrix inverse, multiplied with the gradients. So I should put vector signs here. So I have a vector sign here, a vector sign. So what we're having now is a quantity which depends on the tangent of the variational wave function. So this depends on the delta psi normalized of theta with respect to the parameter, a given parameter here. So what are the consequences? So one consequence, which you will often find, is that there's a reduced sensitivity to redundant parameterizations like Adams, or just using a plain fixed learning rate. Reduced sensitivity to specific parameterizations like Adams, root mean square propagation, specific parameterizations. It often leads to better conditioning, better results actually, or better conditioning in the optimization part. And then you have a close relation with the chosen parameters you have, with the wave function psi, which is now the variational ansatz. Because remember now that this psi, which you see here, this is actually our circuit. Now, there is a lot of other interesting case. So if you now look at the square distance between normalized states, this is actually a connection to the natural gradient. So let me just bring that up. So connection with natural gradients. So let me just mention that. So if I look at the square distance between normalized states, between nearby normalized states, this is actually given by a Riemannian metric in a parameter space. So this distance is normally given by the sum over ij, and then I have this matrix, which is this covariance matrix between the log derivatives of d theta j and d theta k here. So the steepest descent in that metric means that if you do a steepest descent, then steepest descent, this is just an aside. So steepest descent in this metric, gives us a parameter delta theta, which is proportional to minus s inverse times this vector g, which is exactly what's normally called the natural gradient update. So this stochastic reconfiguration, which we discussed now, is the kind of natural gradient method which is specialized to variational quantum states. So basically what we have then, when we collect everything, so we have a recipe where we can calculate this as an expectation value of log derivatives of the tangents of, so that's the tangents of the wave function, and it gives us a metric which allows us to compute the gradients following the expression which we have for the trial wave function. So keep in mind that now we did everything for the energy. So this is the gradient which we get if we take the calculated derivative of the energy as a function of the variational parameter. Now, if you replace the energy, which we have here, with what we want to get from a neural network, the only thing which we need then is actually to replace this quantity with the new type of observables. So if we go back a little bit, the type of observable which we are interested in depends on the type of network which we are dealing with. So if we now go back a little bit to the beginning of the lecture, you remember that the way we set up everything in terms of a qubit case, so we had a encoding part, which when we calculated the energy in the VQE, we didn't need to care about. Then we have the variational part, which is this one. And in the VQE, the observable which you had here is actually the expectation value of the energy. So in those expressions which we got for the gradients, I had the expectation value of the energy and its derivative with respect to the parameters. And when we do a quantum neural network, we now need to look at the encoding part, okay? So we have looked at this way to update the gradients. And as I said, you can, if you want to, and this is something which you can test if you are interested in that in the second project. When we now look at the standard derivatives which we have, you can simply run it by setting up the gradient, by using the parameter shift rule. And when you have the gradients, you can simply just choose a learning rate and do the optimization by classical algorithms. And the nice thing with these quantum neural networks is that for the parameter shift rule, we actually have exact gradients. Because everything here, all the parts of the variational circuits is given in terms of rotations, including Pauli matrices. And Pauli matrices are pretty nice when it comes to the parameter shift rule, because then the parameter shift rule is exact. So this is something which we haven't proven in this course. I'm just stating that. So this is one advantage. And clearly, if we now want to link more information on the calculation of the derivatives, we can then calculate the natural gradient, or what's often called in quantum mechanical Monte Carlo methods, like variational Monte Carlo, diffusion Monte Carlo, it's called stochastic reconfiguration. And that does a much better job, normally, than applications of things like, let's say, Adams or whatever. Because here you have explicit dependence on the trial wave function. In our case, this is the parameterized quantum circuit. Okay? That makes sense? So this is a kind of lesson which we can take from this. So what I want to do now is to go back a little bit to the slides for this week before we jump back to the Jupyter notebook and look at the implementations. So let's do that. And I see now, due to time, that this is something which we will continue discussing next week as well. So let me just quickly say what we have been doing. So this is roughly a summary of what we have. So this would be a typical circuit. So we have an encoding part, we have the variational part, this is the ansatz, and then we have the observables. And the benefit of a quantum neural network is that the variational part often has much fewer parameters than we have in a classical one. And then we have the parameter shift rule, which is exact. And then we have this quantum Fisher information, which comes actually from the calculation of the which comes from the calculation of the classical rule. And the quantum Fisher rule is actually, and you recognize the log derivatives, which are these quantities. So this is actually the covariance. And we use this time-dependent variational principle to actually develop these quantities. And the natural gradient gives us the inverse of this times the cost function. Now, there's something which I will not touch upon, which has been a problem with the training of these quantum neural networks, and that is a problem of barren plateaus, where actually the derivatives flatten out, and then clearly training stops off. Now, in the slides, I actually put in a link to the barren plateaus and the derivatives of the cost function. Take a look at that. We will not discuss it in the lectures this year. So this is a technicality, which is also a very important technicality because it's a problem with the training. Like you have vanishing gradients and exploding gradients in standard neural networks. So basically, if we now summarize a little bit and want to make a link with physics-informed neural networks, so this would be a typical loss function. And in the Jupyter notebook from last week, if we get time today, we will look at those codes. In the Jupyter notebook from last week, I have an example of this cost function where I simply train the fit of a polynomial and compare that with a standard multi-layer perceptron model or standard feed-forward neural network. So here you learn a mapping from observations, and there is no physical constraints which are being enforced. So that's just a discriminative quantum neural network. And the big difference between the classical one is now that the depth of the network depends on how many variational parameters and how many rotation gates you implement. And you will typically see in the example from last week that we actually end up with much less parameters than a standard standard feed-forward neural network. When we make the jump into physics-informed quantum neural networks, then obviously the input are the collocation points. I don't know if you know the word collocation, but these are the points where you want to calculate the value of the function of. That's what a collocation point is. And the loss function is then a part here which contains the residual. We are coming back to that. So the residual is then the difference between the left-hand side and the right-hand side squared. It's a norm 2. So often when you look at these norms, and if you don't see anything as a subscript, it's normally a norm 2. So this is a norm 2 squared, and B stands for boundary, and you can add also the initial conditions. So you're not limited to have boundaries only, but you can also have initial conditions. So encoding. This is the next topic, which we announced at the beginning of the lecture. So the encoding part is actually pretty tricky. I actually find that the most difficult one with the implementation of a quantum neural network. Because the variational part, as we said, I mean, it's just a chain of rotational gates and C0 gates, which entangle the qubits, and then we optimize in the way as we did before. So the way you do that, this is normally called a feature map. It depends on what functions the circuit can represent, the induced kernel on the data space when you make transformations, and also clearly the gradient norms depend on the feature map. So the encoding then becomes part of the model. So it's not like when you do a standard feed-forward neural network, you have the input layer, that's fixed normally. But now the encoding is actually a part. The way you choose to encode the data is actually important. So choosing it well is as important as designing the variational ansatz. And for PDEs, this encoding also determines which spatial frequency the circuit can actually resolve. So when we move on to quantum neural networks for partial differential equations, then it becomes important what kind of spatial frequencies of spatial data we want to resolve. So this is the first one, which is what I normally call the brute force one. And this is called just a basis encoding. And so you have a basic idea, you map a binary string with zeros and ones to the computational basis states. So think of you having this MNIST, scaled down MNIST images with 8 × 8 pixels. So in total, you have 64 pixels. So that means that X1 goes up to, from X1 up to X64. That is your input in a classical feed-forward neural network or convolutional neural network or whatever you're interested in. And then what we did for those of you who took a course like the Physics SDK 4155, we had something which was called one-hot encoding, which is essentially us transforming that into a bit representation, the pixels. So that means that you would start in this tensor product of states, zero qubits, and then you would apply the xi, the NOT gate, on qubit I, wherever xi is equal to 1. So that's an X gate. So if you go back to the very beginning here, you see that we have an X gate here. Because the X gate is the one which acts on these states, and it simply tells you whether it's bit 0 or bit 1. Okay? So that's the first step. The properties is only, you have n gates. So this is the depth. It's one operation on each qubit. So one operation here. But then the drawback is that it requires n qubits for n bits. Okay? So if your problem is of the type where you can do that, then it's okay. So suppose, for instance, that you have 2 particles in 2 dimensions, then you need actually 4 bits or 4 qubits to represent xy, particle 1, and xy for particle 2. So that's a case where you could actually try it. But if you have an image like any image with, let's say, 200 × 200 pixels, this is just beyond what you can do. So you really have to scale it down. And as one of you mentioned during the break, if you look at some of the applications of these algorithms, they are typically done with some few qubits and up to 10 logical qubits, which is basically a very toy model-like case for, let's say, image recognition, which is one of the, how to say, more interesting cases. So it requires n bits, And you have a superposition. You need to encode n strings. That means log n qubits if state preparation is efficient. And this is not suited if you have continuous features for, let's say, a partial differential equation. So if partial differential equations is the interesting topic, forget about it. But if you have a very simple case, well, let's say, where you can get away with 4 to 10 qubits, then you can actually run this type of calculation. There's something which is called angle encoding. So this is just a list of types of ways to encode the data. And the idea here is that you encode xi into the rotation angle of a qubit I. So that means that you would have a tensor product of all these rotation matrices of y. And then you have a rotation matrix for k, x, y, z. And this is typically the type of rotation which you would get for y and z. And you have one feature per qubit. So that means that n is equal to d. You have a product state. There's no entanglement yet. Entanglement is added by 2 qubit gates in the variational layers. So keep that in mind. So the output then is typically a Fourier series in X with frequency determined by the generator spectrum. So this is one way of doing it. You have another one which is called amplitude encoding. So you can then embed this X into state amplitudes. So we then would have a linear combination here. So if you have n qubits, then you can encode 2n features, and that is what normally called exponential compression, and it exploits the full Hilbert space. Challenges: the general state preparation requires quite many gates to do that. So that's one of the drawbacks. And you have a normalization, and if you have n data points, need actually n circuit runs. So the bottleneck here is the readout. The exponential compression does not automatically give a speed up, and reading out all the 2n amplitudes requires exponentially many experiments. So this is a kind of fundamental quantum readout bottleneck, which is relevant to if you're doing quantum physics informed neural networks. So that is one of the bottlenecks. You have also something which is called a structure feature maps, which I just included. I have not tested that, so I'm not sure how it works. So I just leave it here just for the sake of completeness. You have data re-uploading, which is also something which I haven't dealt with. And you can find a reference here. So you can see that this is actually a topic which is an active research field if you want to do quantum machine learning. Another very important topic is also that which deals with baryon plateaus and how to circumvent them. So these are the type of data encoding which are actually being used. And typically, you would often see this kind of encoding in terms of something which leads to Fourier frequencies up to a specific frequency. So these are quantities or ways of encoding the data, which are often used with the solution of differential equations. So I tend to have examples from differential equations because that's the kind of world where I have been living in. And if you want other ones, then it's clearly something which I haven't tested these methods to seriously to image recognition or other cases. Now, the thing which you need to do then, if you look at the parameterized circuits which we discussed, it's a product of all these kind of rotation matrices, where the PJs are different Pauli matrices. And the PJ squared is, as we know, is equal to the identity matrix. So this should actually be, this symbol went wrong. So this is the identity matrix. Yeah, it doesn't look like that. And the typical quantity, if you now think back to what we had in project one, what we ended up with was a quantity like this. This is essentially what we calculated. And the parameter shift rule is an important quantity. And it generalizes if you have exact eigenvalues plus minus r, you can really set it up in terms of analytical expression. So you have exact. And there are only 2 circuit evaluations per parameter, as we had when we did the VQE. So The nice thing with these quantum neural networks is that, except for the encoding, it's so close to what we did in Project One. I hope you see that. And you can also calculate second derivatives. And these second derivatives, which you see there, that's actually used in this stochastic reconfiguration or the quantum Fisher or the approximation to the Hessian matrix, which gives us a better optimization, actually. You will see that when you compare codes. If you look at the codes from last week, you will see clearly that the natural gradients give a better formula. Yeah, I'm going to skip this one because this is just a somewhat repeat of what we went through. The barren plateaus is also something which I will leave out because I haven't done any research here, so I'm just simply stating what I found in scientific articles. And some of the people who have actually been leading this field is a guy who connected with the Google Quantum Project, Jared McLean. And there is a very bright young scientist. Her name is Zoe Holmes, and she's an assistant professor at in Lausanne at the EPFL. And she has actually been one of the leading people when it comes to the studies of barren plateaus. So this is something which I will not say anything about because it's a little bit beyond my cup of tea. So what I wanted, I see that time is running out. So I will pick up these things next week. And I will discuss then the codes in more detail so that we will look at the codes from last week and this week. Next week in more detail, because now we have some of the background theory. And then I just wanted to link, and we will do this next week, link the classical pins with the quantum mechanical pins. So the typical loss function, which you do then, when you set up a neural network, is that your wave function is replaced by the neural network. And you will have terms where you can have a quantity here which contains the boundary conditions. This term, which you see here, will often be given by the difference. So this is the residual, which is the difference between the left-hand side and the right-hand side. And we are going to set up more details next week. And you could also add in here a term which contains the initial conditions. So B stands for boundary conditions here. So LB is one part. This is the residual. R stands for the difference between the left-hand side and the right-hand side squared. And N here is just you having a neural network as an ansatz. And I know that some of you are already pretty familiar with the physics-informed neural networks. Now, one of the problems when you calculate the energies is that a pins is not variational for the energy. But for other variables, it can be. But this is something which needs to be tested. So typically one of the benefits when you solve this type of equations is that you have automatic differentiation, and that makes life very easy. And the classical neural networks normally learn the low frequency components much faster than high frequency ones. And that is a motivation for quantum pins with explicit frequency spectra. And the example we are going to look at are the Poisson equation and also the heat equation. And then there are some slides at the end here about the Schrödinger equation. So what I want to do next week is actually to conclude this part here with a discussion of codes and examples on how we can use quantum neural networks to study specific differential equations. And if we get time, I wanted to say something about quantum Boltzmann machines, which is a generative quantum machine learning method where you actually generate a probability distribution. Now, you can say that the neural networks, when they're used as pins, are no longer strictly discriminative. So if you think of a discriminative machine learning method, you're then training, let's say, a set of images, and you want to make a prediction whether that image is a cat or a dog. So you discriminate. And in the traditional sense, a deep learning method is not used to generate a probability distribution. You can generate errors by just rerunning your network again and again. That's the brute force way of setting up expectation values and variances and standard deviations. But when you solve a differential equation, a neural network can actually be seen as a generative method because you generate a solution. And if you do quantum mechanics, your solution squared is a probability, or is proportional to the quantum mechanical probability. So when you solve Schrödinger's equation with a quantum neural network, you're actually turning a discriminative method into a generative method because you actually get a probability, which is your wave function squared. So there is a floating transition between discriminative and generative methods. So even if people say that the standard deep learning methods, like neural networks, convolution neural networks, etc., are purely discriminative ones, when you solve differential equations, this distinction becomes a little bit more floating. So next week, I wanted to wrap up many of these ideas and go through the codes. And these are the codes from last week and this week. So then I want to discuss them, and we're going to wrap up. And if we get time, I was thinking that we could have the last lecture that will be May 20, I think. Yeah, May 20. Then we can do a summary and perhaps say something about quantum Boltzmann machines. Or maybe we just stop next week. Let's see what happens. But next week, I actually wanted to say a little bit about this quantum neural networks. Okay. So let's stop here.